Hi all, I'm Elif Zeynep Emir from DigiMODE. I'm the sales director of the company. Today I will do the presentation about our extended abstract. I want to share my screen and continue. Actually, I want to mention about myself a little. I have been graduated from math education from the university. Then I got the master degree of engineering management. We prepared an extended abstract for inlet geometry design for gas flow in powder bed fusion process. In this study, we work with Satış, which is the first and one of the biggest camshaft production company in Turkey. Satış also has a very serious experience in machinery and medical industries. In this study, we also work with Professor Oğuzhan Yılmaz and Enes Gebel from Advanced Manufacturing Technologies Research Group. First of all, we defined the requirements for the study. We determined that sweeping of flying powders, the least effect of powder on the table from sweeping process, protection of optical equipments from fume, minimizing the oxygen level as soon as possible are the main requirements for the powder bed fusion systems to achieve a problem-free production, increase the quality of parts, and ensure the continuity of the system. Actually, to achieve all these aims and requirements, we defined a goal for the study. The main goal was to have a laminar flow in the system. Because turbulence flow prevents us from meeting our requirements. In the slide, you may see one example. This flow belongs to an old gas flow of an SLM, selective laser melting system. As you may see in the picture, 36 hours production makes an incredible effect on laser protection windows. This means that fume also affects the parts quality, system sustainability, and etc. For determining our new designs, we researched some papers. You will see some examples at following slides. In this study, it was shown by the analysis that the instability of jets from nozzles affects the uniformity of gas flow velocity significantly. Several design guidelines were suggested, such as nozzles shall be lower and wider relative to the build plate, and the involvement of the downward flow is essential to avoid the recirculation of welding plumb inside chamber. Another study says that variation in gas flow uniformity have been shown to impact both the value and the range of density and compression strength of the samples tested. Improving the gas flow in a typical system was achieved by redesigning the gas delivery rail. This simple modification reduced the standard deviation of the results significantly, leading to the formation of the component with more consistent and reproducible properties. This improvement in quality also involves the occurrence of what are considered to be thermal lancing issues, which are the subject of ongoing investigation and will be reported in further publication. In another study, it shows that decreasing the cross-flow rate of shielding gas flow below a certain threshold decreases penetration and increases multiple width and instability during the LPBF process. Due to the significance of the vapor plume and the effectiveness of its removal by shielding gas flow in relation to multiple geometry and porosity and LPBF, vapor plume laser beam interactions should be included calculations of models aiming at predicting multiple geometry. The shielding gas flow is an important factor in the LPBF process to be taken into consideration when trying to develop processing parameters for a specific material that could be transferable from one LPBF machine to another. Another study was performed to understand the key design parameters which affected the defined output parameters. It was found that reducing the inlet rail radius had a positive effect on flow uniformity, average flow velocity, and particulate removal. Reducing the inlet radii improved flow uniformity and average velocity, but decreased the amount of spatter effectively being removed, but reduced the amount accumulated on the processing area. Also, moving the inlet and outlet height flush with the processing area improved flow uniformity, increased local fluid velocity, and also removed slightly more splattered particles through the outlet. For our new design for inlet geometries, ANSYS Splend is used to analyze the gas flow streamlines. Operation conditions inside the chamber were taken as 1000 Pascal and 46 Celsius degree. Standard K epsilon turbulence model and standard wall function was used, and inlet velocities was defined as 2 meters per second. Circular hole diffuser directs the air in 2 dimensions and cannot fulfill the volume near the walls. It causes more turbulence in the chamber. However, the design that have planar plates diffuse the air in 3 dimensions and repress the gas to the outlet. It reduces the turbulence volume in the chamber. As turbulence volume increases, the potential of the contamination of laser optics by fume produced during the melting increases. It is clearly seen in the figure that plate-shaped diffuser repress the turbulence and differ flow area in chamber. Those areas occur diffusers inlet, lower inlet, and laser inlet. To protect from contamination by fume, a flow chamber is obtained near laser optics. V-shaped protective flow chamber is obtained more efficiently with plate-shaped diffuser. The angle between plates is investigated. As the angle increases, turbulence volume decreases. In this study, the effect of inlet design to gas flow are investigated. It is obtained that the diffuser geometry affect the gas flow characteristic inside the chamber. Plate-shaped design has been found to be more efficient than the circular opening design. The angle between the plates have positive effect for the turbulence. As the angle increases, V-shaped protective flow chamber can be obtained in an efficient way. Actually, more study and results are on the system which is produced by Satış. Thank you for your attending and listening. If you have any question, please share your email with me.